Okay, welcome back. So far we've seen a typical CNN with a number of layers, the convolutional layer, and the different type of convolutions, the nonlinearity, for example, the ReLU or the sigmoid. And we've seen the pooling layer, for example, the max pool or the average pooling. We've seen also a normalization layer, which comes after the pooling, which was used for the case of AlexNet or the case where you have a ReLU, but it's rarely used. And the idea is we said that the idea is to put these layers in series, and this would give you your CNN model. And then we said that sometimes you have a fully connected layer, just like the multi-layer perceptron, or the softmax layer, which gives you probabilities at the output. And we talked also about the different type of loss functions, and we saw how we train our model to minimize this loss function. Now we're going to, when you train your model also, sometimes you have enough data, but when you do your training, you don't have enough, you don't have a large number of layers. So your model is not deep enough. And you would like to know when it is the case. What are the indicators which tell you that you don't have enough layers? Also, sometimes you have a very deep layer, but then your model does not train well. And you want to know what are the indicators which tell you that you're not training enough. Maybe because you don't have enough data or labeled data, because we're dealing with a supervised network. So for this, we need to talk about regularization. In the case of where we have a deep model and then we don't have enough data, we need to regularize our CNN. But before we talked about regularization for CNN, let's explain what regularization is in the case of machine learning. And let's take an example where you need to fit these data points using a polynomial. So this is a low order polynomial, and you can see that if you try to fit these points with a line, the fitting is not very good. So you can see that the error from the point to the line is large for most of the points. And in this case, you say that you're underfitting. You're not fitting most of the points, so you're underfitting. And then if you increase the complexity of the model, in this case, because it's a polynomial, so you increase the degrees of the polynomial. So you can see that in this case, you're fitting almost every point. And the system so the system is memorizing more than it's generalizing. Well, let's talk about this before, but you're here, in this case, you're overfitting. You're fitting every point. And then you would like, and we'll link also this to the bias and the variance. So in this case, in the case of an underfitting, the case of underfitting, you can see that your training error is high. This is the training error. So you can see that the training error is high, so you have a high bias. So the training error is related to the bias. So if you have a high training error, so you have a high bias. And then when you test your model, you see that you have also a high error. And then the variance, or the difference between the training error and the testing error, is not very large. But bottom line, because you have both high bias and low variance, meaning that you have a high training error and a high testing error. So this is a bad model because it is not able to perform well with the data that it has seen, but when you test it on unseen data, it is also not able to perform well. So this is not a desired model. In the case where you have overfitting, your training error is low, meaning that it is able to learn the data that it has seen. It actually memorizes almost every point. But when you give it new data for when you want to test it, you see that the error is high. So you have a low bias because your training error is low, but you have a high variance because the difference between the training data and the test data is high. And also, so this model here is not able to generalize, so this is not a desirable model. So you would like something in between, okay? So it is fitting this polynomial with this complexity is fitting almost well most of the points, but also if you give it a point that it hasn't seen, it is able to fit it well, as opposed to this point here. If you give it a model with a point that it hasn't seen here, you would not be able to um, predict, you will not be able to fit it well. So before, people used to talk about bias variance trade-off, meaning that if you if you have because what you desired, what you would like to have is a low bias and a low variance. And then people in machine learning before used to talk about the bias variance trade-off, but actually in the case of CNN, we don't have this problem because we can design a system which is deep enough to give us a low bias, but also we can and without affecting the variance, meaning that we are able to design this model to be able to generalize and give us also a low variance. And this is achieved by regularization approaches. So in the case of where you have, for example, a certain loss function that you would like to minimize between the predicted output and your actual output. So that was the previously, that was the kind of loss function that we wanted to minimize. If for logistic regression, for the case where you need to fit these data points to a certain polynomial, you would, instead of just minimizing this loss function, you also minimize, so you're minimizing this loss function to find the weights of your network, of your multi-layer perceptron, for example. But then you would need to, in this case, you would need to regularize it. Meaning what? So your problem is ill-posed, and then ill-posed is either the solution. So there are three conditions for a well-posed problem, according to Hadamard's condition. So the solution exists, it is unique, and it changes continuously with the input. So if your problem is ill-posed, you would need to regularize it. You would need to kind of, instead of searching for the weights in the whole space, you're adding another constraint, a constraint to your loss function to be able to, instead of searching everywhere, you're constraining your search. And in this case, you can do it in different ways. So you have an L2 regularization, L1 regularization, or other approaches. So in the case of L2 regularization, so what you need is you add a term here, which is the norm of the L2 norm of the weights with a certain parameter. And the idea is this parameter here gives you a compromise, but whether you minimize this more than this one also. So this is the regularization parameter. You can use, instead of using an L2 norm, you can use the L1 norm, okay? And this will give you the L1 regularization. So this is in the case of logistic regression, in the case where you're using a multi-layer perceptron, for example. Or now in the case of CNN, if you do regularization with the CNN, you can also use L2 regularization or L1 regularization, and there are other approaches also which are used as listed here on this slide. We'd be interested in the data augmentation, dropout, patch normalization, and early stopping that we've seen before actually. So what is data augmentation? When you have a data set and your model is overfitting, meaning that you have a larger number of parameters compared to your number of labeled data. So in this case, what you do, you augment your data because you don't have a loss of it. So what you do, you perform certain operations. So first of all, data augmentation is a very effective way of enhancing the generalization power of the CNN model, avoiding overfitting. Data augmentation can enlarge the data set. So you make it larger by making several copies from a single image by using certain operations like rotation, cropping, flipping, scaling, and so on. So if you have, for example, a data set which tells you, and you have only one pair, so this image and the corresponding class which says this is a butterfly, but you don't have a lots of data, so you want to also to make sure that your model does not overfit and it's robust to all these changes and so on. So you perform that augmentation by rotating these or flipping this image. You can scale it, you can have shear it, you can have other operations as well. Also color jittering, where you add a little bit of noise and so on. So you perform these operations. And in that case, instead of just having one pair, butterfly and this image and the class, the corresponding class of butterfly, you will have all these set which correspond to your label butterfly. So you have a much richer data set or labeled data set. You augmented your data. The second way of regularizing your network is to use dropout. And this is one of the most popular approaches for neural network regularization. So what you do, instead of having or training this whole model, you assign a certain parameter, so to say that the chance or the probability for this network to fire or to be activated is equal to 0.5. And so when you feed an input, so the chance that one neuron fires or not, so it may be with one training sample, you would this node would fire. In the next training sample, this node would fire. In the second training sample, with the second training sample, this node would not fire. And the same thing for this one and this one and so on. So for each training sample, you're going to change. So going from, instead of having this simple model, or I mean this fixed model, it's going to change. So maybe for one training sample, you're going to have this configuration, this subnetwork, if you want. Another one, you're going to have a different subnetwork, and so on. And that's the way. So sometimes you make this node to allow it to learn, and sometimes and then this node not allowed to learn, and so on. So basically, this is intuitively, this is just like if you you want the model not to rely on the same features for learning all the time. Also, because you're giving it too much, or you're giving this nodes or these nodes too much information. It's just like when I give you, when I give you street directions. If I tell you okay, you have to turn left, right, in with a lots of details, you may not be able to learn the directions, as opposed to maybe giving you enough enough uh, simplified directions, then you would be able to learn better. So this introduces an ensemble effect during the testing phase, meaning that these subnetworks work like um, they perform an ensemble learning, just like um, you sort of aggregating the knowledge that you acquire during the training. And remember that the knowledge, so when you train a model, the information that the model learns is stored in the weights, okay? So another way of regularization is to use batch normalization. So in this case, we normalize the mean and variance of the output activations from a CNN to follow a unit Gaussian distribution. So this is similar to the whitening transform. We've seen that actually before. We didn't give it this name, but the whitening transform is where you normalize the mean and variance of your input only. It's a pre-processing step to make sure that your input has zero mean and unit variance and the variance of 1. So unlike whitening, in the case of batch normalization, you apply it to the intermediate activations. So instead of just taking your input and then normalize your input, you do it in the case of batch normalization. For each layer, you normalize the activation. You normalize the net activation, or you normalize the result of the activation, meaning after you apply your activation function. And this is the most popular approach to normalize. Now, this is something not to confuse with the normalization layer here, which was used because of the effect of using a ReLU. And we said that layer is mostly not used. So this is the normalization of the activation. And then it is very useful for the efficient training of a deep network to avoid overfitting. And the batch normalization operation can be performed as a layer in a CNN. So you can perform it as another layer here. Now this layer is not fully learnable, so you don't learn the parameters of the layer. So how do you perform this batch normalization? So let's say you have at your input values of X of a mini batch. So you have these are your activations, and then what you would like to do is to change these activation to new activation, or to normalized activation Y. And the steps that you follow is you compute, so you take all these activation for that mini batch and you compute the mean, okay? So you sum over M, xi from 1 to M, and then you also take the mini batch variance, and you take, so you subtract the mean, you divide by the variance, so you normalize, but in this case also you add a certain epsilon to avoid dividing by 0 in the case of where you end up with a very small variance here. But also you perform this operation, you multiply by gamma and beta. So you take this normalized output or normalized activation, and you multiply it by gamma and beta. And these gamma and beta, you can learn them, okay? And the idea is if the batch does not really need, if your if your xi does not really need to be multiplied by, or you don't need to subtract the mean and divide by the variance. So this operation here is going to allow you to not do it. Another regularization approach is the early stopping approach. And then we've seen that in the case of the multi-layer perceptron, we've talked about it. So when you're training your model, your training error, it decreases, okay, with the number of training iterations or with the number of epochs. So your training error decreases. But then we've seen that we sometimes, or most of the time, have a validation set that we test. Our error decreases, but at a certain point, we see that our validation error increases. And this is when we are supposed to stop our training to avoid overfitting, okay? So the training algorithm can continue to improve. So avoid overfitting in the iterative gradient-based algorithms. The training algorithm can continue to improve on the training set, and so the performance on the validation set also improves, okay? And these are the different type of regularization or most popular regularization approaches used for the case of CNN. Thank you.